Okay, at this point, you should have all of the information filled out for graphing rational functions that I have shown here. You should have identified your horizontal and vertical asymptotes. You should have found any holes and roots and y-intercepts, and then also looked for excluded values in the domain. So the only thing I'm going to add for you is how to figure out what the graph looks like. So I've plotted everything pertinent on the graph. And let's talk about how to graph the rest of the function. So I want you to notice at the top what happens or what that function becomes after we cancel things. And when we end up with just a 2x minus 1. This should take you back to your Algebra 1 days, and you recognize that this is a line with a slope of 2 and a y-intercept of negative 1. We can see that right here. We already have our y-intercept shown at negative 1. And then the only thing that's weird about this is because it's a rational function, we've introduced a hole into the graph. But other than that, it just looks like a line. So from here, we can plot some points to show the slope, and then we can go ahead and connect those dots as best we can to show the shape of the graph. So for a lot of these, if you find that you have a slant or oblique asymptote, I'm not going to require you to give the end behavior, but after you graph this, you can see what the end behavior is. As x approaches positive infinity, your f of x approaches positive infinity, and then as x approaches negative infinity, your f of x approaches negative infinity. So that one, if you can tell what the end behavior is, then go ahead and list it. Here's example 2. You should have a horizontal asymptote at y equals 0. I want you to notice how I wrote that on the graph. Since it's on an axis, you can go ahead and put those slash marks to indicate that there's an asymptote on the actual axis. Remember, end behavior is going to follow along with that horizontal asymptote. So g of x is going to approach 0 as x approaches positive or negative infinity. We do have a hole at negative 1, 1. How do we get that? It's based on the factors that cancel. And then we find our y value by plugging in what's the x value and then finding what the y value is after you've canceled factors. Then y-intercept is 1/2. Remember, what we do there is you can take off all the numbers that have x's on them and then look at what the constants are left, and there's your y-intercept. So now the question is, what does the graph look like? Well, you can intuitively figure out what the graph looks like at the top right because we have some points there. So there's really no other shape for the graph right here except for this. So remember, the graph won't ever cross or touch the vertical asymptote. And as x is approaching positive infinity, it's going to be approaching that horizontal asymptote. So the second part, what I look at here is if you look at what's left, we end up with a 1 over x plus 2. Notice this is just a rational function that's been translated 2 units to the left, and you can see that shape. So because you know it's a rational function, then you know that the other side has to be kind of in the opposite quadrant as that first side. If you're not sure about that, then your process is to plug in a point. And we can go ahead and plug in a point into that simplified version. And let's just ask ourselves, what would the y value be if we plug in, let's say, a negative 4? And what I'm expecting is that I'm going to get a negative something right there. If I got a positive something, then I would know that my graph would be up on top of that horizontal asymptote and to the left of the vertical one. But let's go ahead and test that out. So we can say 1 over, and then if I plug in a negative 4 plus 2, I end up getting a 1 over negative 2. And so basically what this is saying is the point, if I plug in a negative 4 in for the function, I get a negative 1/2 for my y value, which is the point, I guess, a little bit higher than what I have it drawn like that. But what it indicates is that the graph is on that side of your horizontal and vertical asymptotes. All right, let's move on to the next one. So for example 3, there are no factors that cancel. So notice we have no holes. We do have a horizontal asymptote of y is equal to 2. The end behavior matches that horizontal asymptote. We have a vertical asymptote determined by the factors in the denominator that don't cancel. So we have a vertical asymptote at x equals 2 and x equals negative 2. Roots come from these factors up here. And so we have a root at negative 3/2, 0, and a root at 1, 0. And then finally, if we eliminate all the terms that have x's on them, we're left with a negative 3 over negative 4, or positive 3/4 for our y-intercept. Ordered pair is 0, 3/4. And then for our domain, we can't have an x equaling positive or negative 2. So what I've drawn on my graph already is I've shown my horizontal and vertical asymptotes. I have labeled my roots in red and my y-intercept in blue. What that helps us do is we know that those yellow lines are boundaries, so we know for sure that this graph in the middle is going to be that shape. Now we have the middle of the graph figured out, but we need to figure out what the left side and the right side of the graph look like. We really only have 2 options. The left side can look like this, or this, because we know that as x approaches infinity or negative infinity, it's going to approach that horizontal asymptote. And then the right side can only look like this or this. And what's nice about this is we don't have to plug in points, because I want you to notice that there are no roots on this side of the graph here or this side of the graph. What that means is that the graph that would be down here, those are not possible, because if they were, we would have a root show up on both sides. So just by process of elimination, basically, we can say that the graph has to have a piece of the graph on the top right and a piece of the graph on the top left. So your backup is always plug in some points, and you can plug in like a point of -3, for example, and make sure that there's a point that's up here to go with it, and you can plug in a +3, and again, check and make sure that the point is in fact above that horizontal asymptote. But always look for ways that you can go, oh, it can't be here because there's no root. All right, next question. This one's a little bit trickier. Just know that it's not a bad thing to plug points in to figure out where your graph is. So I've gone ahead and I've factored the numerator and denominator, and I've canceled common factors on top and bottom. I have a horizontal asymptote at y = 0. Why is that? It's because the degree on the bottom is bigger than the degree on top. So remember, bigger below y = 0. So our end behavior matches the horizontal asymptote. We have a hole that's determined by those two factors that cancel. So our x value of our hole is -3, and then we would plug in a -3 here, and a -3 here, and a -3 here to find our y value. So our hole is at -3 and then 1/4. We have a vertical asymptote determined by the factors that don't cancel on the denominator. So a vertical asymptote at x = 0 and x = 5. We have a root determined by the factor on the top that doesn't cancel. So we have a root at 3, 0. Here, notice there's nothing on the bottom that's a constant. So we end up having an asymptote taking out a y-intercept right here. So we have basically a -9 over 0. So we don't have a y-intercept there. And then finally, we have restrictions on our domain. X cannot equal 0, 5, or -3. So the only thing we have left is to graph. Now, we know what the graph looks like to the left of the vertical asymptote and above the horizontal asymptote. It has to be like this because we have a hole there. On the right side, I'm going to go ahead and plug in a +6 for my x. So let's do that. So if I do 6 - 3 times 6 + 3 over 6 times 6 - 5 times 6 + 3, we end up with, this is a 3 times 9, so a 27 on top. On bottom, we have a 6 times 1 times 9. 6 times 9 is 54, and we end up with a 1/2 right there. What that tells us is that the other side of our function right here is going to have to be on top. So the tricky part here is what that middle looks like. Remember from the definition of a horizontal asymptotes are mostly for the purpose of helping you see the end behavior. So as x approaches infinity, then the function is going to approach the horizontal asymptote. But in the middle, where you're not approaching like either positive or negative infinity, graphs can cross horizontal asymptotes at times. So don't just automatically assume that the graph looks like this or that the graph looks like this. Because the reality is the graph could look like this, or the graph could also look like this. So what we're going to need to do here is we're going to have to plug in points on the left and the right side of that root. So let's do that. Let's plug in first a 2. So if we plug in 2 for x, we get 2 - 3 times 2 + 3 over 2 times 2 - 5 times 2 + 3. So let's simplify from there. This is a -1 times 5. So a -5 over, this is a 2 times -3 times 5. So 2 times -3 is -6. -6 times 5 is -30. So we end up with a +1/6. That means that the point, remember it was a 2 for our input, and we got a positive number right there. So we know that on the left side of the root, that the graph is doing this. So now let's see what the graph is doing on the right side of the root. Let's go ahead and we'll plug in the point 4. So if we plug in 4, we get 4 - 3 times 4 + 3 over 4 times 4 - 5 times 4 + 3. So let's simplify from there. So 4 - 3 is 1, 4 + 3 is 7. So we end up with a 7 over. This becomes 4 times -1 times 7. So we get -28. So this is a negative 1/4. So at 4, we have this point. We have 4 and then negative 1/4. So that means that this function actually passes through or crosses the horizontal asymptote at that root of positive 3, 0. And the last one, it's already factored for us. We do have a horizontal asymptote of y equals 1. Why? Because if the degrees are the same, then we just have the ratio of the coefficients for our horizontal asymptote. The end behavior matches the horizontal asymptote. We have no factors that cancel, so no holes. We have a vertical asymptote that's designated by the factor on the denominator that doesn't cancel. So we've got a vertical asymptote at x equals negative 1. A root comes from the numerator, so root at negative 3, 0. A y-intercept, remember, we're going to eliminate the terms that have x's, and we can say this is negative 3 over negative 1. So we have a y-intercept of 0, 3. And then our domain restriction is that x cannot equal negative 1. All right, so now what we can see here is because we've got an asymptote and we have a y-intercept, then there's no other possibility for the graph on the top right except for that. And the same is true for the bottom left. Is because we have a root right there, then our graph has to look like this. So a little bit of an easier one to end the video.